Hello everyone, welcome to the Equilibrium Vodcast for Chapter 15, Number 1. Let's talk about the concept of equilibrium that you've been working with in lab for the last week or so. Equilibrium is the concept of a reaction that can go forward and reverse. And equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. We can see this with the example of the reaction between nitrogen dioxide and N2O4, dinitrogen tetroxide, breaking down and forming nitrogen dioxide. You can see in this reaction that the amount of N2O4 decreases as the amount of NO2 increases. But the N2O4 doesn't disappear completely, and it remains at a constant concentration, as does the NO2 at some point in the reaction. So if you look at the rates, the N2O4 is slowing down in its decomposition. The rate of decomposition is slowing as the rate of increase, rate of NO2 is increasing. Excuse me. When they reach an equal rate of breaking down and forming, then we have reached equilibrium. The conditions of equilibrium include that both the forward and the reverse reactions must be occurring at the same time. They must be proceeding at the same rate to be at equilibrium. And the amount of the products and the reactants don't change once equilibrium has been established. All right, so we want to be able to write a reaction as an equilibrium reaction and as an expression so we can look at it quantitatively. So if we were looking at that same reaction of dinitrogen tetroxide decomposing into nitrogen dioxide, we would have double arrows, a forward and a reverse. When you want to make this a quantitative relationship, you have to note that both rates are happening at the same time and they're happening at equal rates. So let's describe the rates. For the forward reaction, assuming it's an elementary reaction, we've got N2O4 breaking down into 2NO2. The rate law for that, as we've learned, is rate equals forward reaction rate constant times the concentration of N2O4. For the reverse, it's 2NO2 yields to N2O4. And its rate for the reverse would be a new rate constant times NO2 squared. Since we know that they're equal to each other, the forward and the reverse rates, we can set them equal to each other. Now, if we rearrange so that we have the concentrations on one side and the constants on the other, we get this. So we've got the product raised to its coefficient divided by the reactant. That will equal the ratio of the forward to the reverse. Sorry about that. And that is a constant called the equilibrium constant, KEQ. EQ is a generic descriptor of an equilibrium constant, and it's used most of the time in settings when they're using the concentration as the unit for equilibrium. Concentration being depicted by the brackets here, concentration and molarity. All right, let's apply this directly to the Haber process. You watched a video about this really interesting and very important process in which ammonia is made from nitrogen and hydrogen. And that was so challenging because it's an equilibrium reaction and the ammonia starts breaking down back into its reactants. And so Haber figured out how to make that profitable. So we would write its equilibrium constant as the concentration of ammonia in molarity squared divided by nitrogen concentration times hydrogen concentration cubed, using the coefficients for the reaction. And I've labeled that case C here. You'll sometimes see that C being concentration. So we can generalize this now so that you can write an equilibrium constant for all equilibrium reactions. You would put the products in the numerator over the reactants in the denominator, raised to their coefficients. You can do this with concentrations or with pressures for gases. And when we use pressure, we'll use atmospheres, and that'll become important in a little bit. This is how it would look if you were writing it as pressures. So let's write some equilibrium expressions for these three examples. So pause the computer and try to write these out on your own, and then I'll come back and I'll show you the answers. So for A, you've got oxygen cubed divided by ozone squared, NaCl squared over NO squared and Cl2. And C is silver diamine ion concentration over silver ion and ammonia squared. All right, there will be some more information we'll get as we go along, but anytime you have aqueous compounds, you use concentrations. If you have gases, you could use concentration or you could use pressures. And solids we leave out because solids will not influence equilibrium of gases and solutions if there's solid available. Their amount won't change relative to the reaction. Talk more about that later. All right, so let's go back to that fact that we can use concentration or pressure. So from the ideal gas law, hopefully you remember that PV equals nRT. You can rearrange that to solve for P, and this shows us how pressure is dependent on concentration, because concentration is moles divided by volume, and then times RT. So if we stuck this into an equilibrium expression, I might want to rewrite this as molarity, which is N over V, would equal P over RT. So you could put that into an expression in place of the concentration. Or we could put all of this in for the pressure if we did it by pressure. So if we had the pressure equilibrium, it would be all of the concentrations that would make up a Kc times RT. So if this is a concentration right here, you take it times RT to replace the P. So let's say we had Kp equals pressure of D raised to the D over pressure of A raised to the A. Not going to use 4 things, just use 2. So I'll put in, let's say, concentration of D, which represents this N over V, raised to the D, but then also times RT, the gas law constant times the temperature. And this would be concentration of A raised to the A, this one's raised to the D also, times RT raised to the A. So I could simplify this by showing that this whole part right here of the concentrations is the same as the equilibrium concentration by concentration. So I'm going to symbolize that with this part, times RT raised to the, now if we're going to take RT raised to the D divided by RT raised to the A, it's RT raised to the D minus the A. And we could simplify that The D minus A is what is represented here by the delta N. And delta N is the moles of the product, which are going to be in the numerator, minus the moles of the reactant, which are in the denominator. Now, R in this particular case is 0.0821 or 8206 to be more precise, atmospheres, liters per mole Kelvin. This is the gas law constant for the atmosphere unit, which is what scientists agreed to do equilibrium constants in that unit. So you'll use 0.0821 or 0.08206. Let's go through an example of this math. So for that Haber process, need to put in some arrows. Here's your equilibrium reaction. We know that Kc is 9.6 at 300 degrees Celsius. So let's calculate Kp at that temperature. Now, if you notice those units on the R value, again, R was 0.08206 liter atmospheres per mole Kelvin, then you should remind yourself that you have to use the temperature in Kelvin. So at this point, pause, calculate this problem, and come back. The answer should be 4.43 times 10 to the negative third. Here is your Kc value, and it's R times temperature in Kelvin, all raised to the negative second. So this is just rewritten so that that's a positive exponent. Okay. Now let's look at the same reaction again. N2O4 yields 2NO2. And write the equilibrium expression as Kp. Here's some data for this reaction, and it shows that the value of the constant is 6.46. Now we're going to just look at this examples, or experiment 3 and 4, because experiment 3 starts with no dinitrogen tetroxide and forms NO2, and experiment 4 starts with no NO2 and makes the N2O4. And if you notice, the point of this slide is that no matter which direction you reach it at, it ends up being the same value, 6.46. In summary, equilibrium expression depends on the stoichiometry, does not depend on the mechanism. The value of the KEQ depends on temperature, so you have to have a different KEQ value for every temperature at which the reaction will occur. And you omit the units for the equilibrium expression. Think of it just as a ratio of the forward rate as compared to the reverse rate. All right, so what does the size of that number mean? The K value. So as we showed in our example, our simulation in school, if you have different rate potentials, you'll end up with different amounts of substance. So in this particular case, the forward rate is exceeding the reverse rate. So it says the equilibrium lies to the right, and the K is much larger than 1. You're going to get more products. If you have the opposite situation in which the reverse rate has a greater potential than the forward rate, then you're going to have a K much less than 1. So those numbers can tell us something about the reaction. Okay, and now we can change the actual K value, thinking about the reaction going at different rates. Because you can write a reaction that's in equilibrium with one chemical being the reactant, or with the other chemical being the reactant. It doesn't matter, that they're reversible. So the one that's on the left is irrelevant. You just have to make sure that you communicate which one is your reactant and which one is your product when you're describing these reactions. So if you notice, when you have them going in opposite directions, as we saw before for the Kp, for this reaction, you get 6.49 or 6.46, maybe, one of the two. But if you reversed it, how do you suppose that's going to compare to this one? Everything will be flipped over, so the value is also flipped over. So if you took 6.49 and inverted it, you would get 0.154. So again, the reverse of a reaction is the inverse of the Kp value. Let's look at some other things that can change the Keq value. So to find the new equilibrium constant of a reaction when the equation has been multiplied, such as N2O4 yielding 2NO2, changing to 2N2O4 yielding 4NO2, as you might have to multiply a reaction if you want to combine it to get a mechanism, or a Hess's law problem requires multiplying. Let's see how that affects the equilibrium constant. So if you write the first one as actually that should be Kp, sorry. These should be pressures. The pressure of NO2 squared divided by the pressure of N2O4 is 6.49. And the pressure of NO2 to the fourth times divided by the pressure of N2O4 to the second will give you 6.49 squared. Because the exponents are squared, your answer is going to end up being squared. Now, we might have a situation where we have to add equilibrium reactions together to get an overall reaction if they're part of a mechanism. So, for instance, if we have two different equilibrium constants, you find the product of them to find the overall equilibrium constant. So let's say we have a first reaction, 2NOBr yields 2NO plus Br squared. Then you've got that bromine that was produced reacting with chlorine to make 2 BrCls. Now if you notice, the bromine is an intermediate. It would cancel out. So you can write an overall reaction of 2 NOBr plus chlorine yields 2 NOs plus 2 BrCl. So to calculate the equilibrium constant for these two reactions combined, you take K1 times K2, and you get 0.014 times 7.2 to get 0.10. All right, so now I've got a practice problem for you to do. If you have HF yielding hydrogen ion and fluoride ion with a Kc value of 6.8 times 10 to the negative fourth, oxalic acid yielding hydrogen ion plus oxalate ion with Kc equals 3.8 times 10 to the negative sixth, try to figure out a way to combine these to produce this overall reaction. Now, you may have to do more than just combine them directly. So look and see if you need to reverse anything or multiply anything and go from there. Pause, solve that, and then come back. Okay, let's see how you did. All right, notice the first reaction needed to be multiplied by 2 so that you have 2 HFs in the equation. Then you have to take the Kc value and multiply it by 2. The 6.8 times 10 to the negative fourth times 2 becomes 4.6 times 10 to the negative seventh. The second reaction had to be reversed so that the HFs could cancel out and you'd get oxalic acid as a product, which is where you want it. So for this one, you had to invert it. and you get 2.5 times 10 to the 5th. Once you have that figured out, you just multiply them together and you get your answer of 0.21. That's enough for today, folks. Please fill out the summary form and fill out your notes outline